All right. Hello, everyone. We're going to go over section 5 today. We're looking at properties of estimators, of basically of estimates of parameters that we're interested in. This is important because a lot of the concepts that we use here are going to show up throughout the rest of the semester. And in fact, they show up all the time in statistical and machine learning literature. And so we're going to look and try and understand precisely what some of these things are. There are some basic criteria by which we judge an estimator of theta. So the target of interest here, target of interest is this guy here. That's theta. Theta can be a mean, can be variance, can be an area under the curve, can be sensitivity, specificity, could be calibration, could be all sorts of things. And our estimate is that guy. That guy's theta hat. So theta hat is an estimate of theta. And very often, theta hat is a function of the data. We just don't always write it because it's extra notation. We don't need it. So all the data, everything's in theta hat. For example, X bar is a theta hat. In that case, theta might be mu, for example, right? The expected value of X bar. So the things that we pay attention to are bias, variance, mean square error, and consistency. These are the major criteria by which we judge an estimator. And so let's talk about each. Bias has a very specific term. Bias is whether or not your estimator is equal to the true thing on average. And this is important because we're talking about average properties. So is your estimator on average equal to the thing that it's supposed to be estimating? Now, what does that mean on average? That might mean you do experiment 1 and you get an estimator. Then you might do experiment 2 and you get an estimator. You might do experiment 3 and you get an estimator. You do experiment 4 and you get an estimator, etc. And if you took the average of those things, then they're going to be centered right on the thing you're trying to estimate. That's bias. This is the fancy definition right here. And very often, just to remind everybody what it is, I'll write little b of theta hat. That's the bias. Of course, the other thing is not just bias, right? You might be off a little bit on average, but you want to know what the average is, right? I'm sorry, what the variance is. So you can say, well, what's the variance of the thing I'm estimating, right? So bias and variance together make up quite a bit of the qualities that we're looking at. And so the variance of an estimator here is given by this formula. It's the standard variance formula. And if you think about that a sampling distribution, your sampling distribution might look like this. And this is the sampling distribution for theta hat. So you've got all your theta hats here. What you'd like is for that thing to be centered square on theta. But also this distance here is governed by the variance. And so what you really like when you get a lot of data is for this thing to be super tight right in there. So that's bias. I'm sorry, that's variance. You can combine bias and variance together for mean square error. Well, what is mean square error? Well, mean square error is this thing, and this is an important type of quantity. It comes up all the time in statistics, in machine learning, in economics, comes up everywhere. And this is how far your estimate is from the truth on average. But I can't just add all these things up straight up because you might be above, you might be below, they'll cancel. So I add these things up squared, right? So notice that this almost mean square error almost looks like a variance. You can see here that this piece right in here, this looks almost like this. And so if in fact your estimator is unbiased, that means your expected value of theta hat is theta, then variance and mean square error turn out to be the same thing. But if you're a little biased, then mean square error is going to turn out to be the bias plus the variance, and we'll see that in just 1 second. The last thing, the last one that's important is this quantity called consistency. Now, I think consistency is one of the most important quantities that you can evaluate, but it's a complex one, but an important one. Consistency essentially says if you had all the data in the world, would your estimate end up being equal to the thing that you're interested in? This seems to me to be like a good proof of concept. If I had all the data in the world and I did my analysis and I calculated my estimator and I still can't get the right answer, then why would I ever get the right answer with less than all the data? So consistency says, okay, if I take my estimate and I add lots and lots and lots and lots and lots of data, where does it end up? It should end up at the truth. And back when we were looking at various things, remember we were looking at X bar and we looked at all those paths and we saw, oh yeah, X bar, if you remember, X bar is the sum of the Xi's over N. So we're scaling the sum in a way that all of these paths come together. They all come together at the expected value of X bar, which is mu if you're from a normal distribution, or theta in this case. And so they all end up right here. So you end up exactly where you're supposed to end up. So consistency is important because it tells you your estimator is really a good target for what you're interested in. Okay. And so we're going to try and put all these things together with some examples, but these are the main criteria. Consistency is the hardest to judge off the bat. There are certain classes of estimators that tend to be consistent for the thing that you're interested in. And so those procedures and estimators are good to start off with. But if you don't have a model or some algorithmic approach that where the consistency isn't already established, then you need to just go figure out whether or not your estimators are consistent. And you can do this mathematically, or you could just do it by simulating with a long stream of data and seeing how close you get. So let's take a look here and let's just back up 1 second and let's take a look at the mean square error. Here's the mean square error. And here's the definition of the mean square error, okay? And that in there, remember, is we think about it as the expected value of theta hat sometimes. And that's when that's equal to that. Actually, I'm leaving it general, so let me just erase that for 1 second. And let's just follow. Let me not get ahead of myself here. Let's just follow what's going on. So mean square error is how far the estimate is from the target on the squared error scale on average. And what I'm going to do is I can take this and I can reduce that. Forget the first two steps here and go to the last step. This turns out to be the variance plus the bias squared. So if in fact the bias is 0, so if the bias is 0, then the mean square error is equal to the variance. So we get a good sense of the mean square error is measuring our variability. How far are we off the target? What's our variance, right? The variance and bias. One of the reasons that this is important is you can imagine, let's suppose here's our target. Okay, here's our target theta. But here is where the expected value of theta hat is. So this means that all our estimates end up around here. And so we have a little estimate. And this can happen with biased estimators. So this is a biased estimator. It's a biased estimator. And so I want to know, well, what's the variability? What is the variability in theta hat? Well, I've got this variability to add up, but also I'm not even close to the truth because this is the truth. This is where I want to be. So I have to take this first part of the variance and add the second part together, and mean square error measures that. That first part is here and that second part is here on the squared scale. So I sort of add up how far is theta hat from theta on average is essentially what I'm asking for. We can go through this derivation. I'm not going to spend a lot of time on it, but you can expand this quantity here, and see I'm adding 0 because those cancel. And then I multiply cross product, of the two terms. And I get this particular thing, and this explains how we do it. It's good if you can follow those steps. Those steps are important, but it's not critical at this stage. Understanding if you could draw, for example, this picture right here, the one that I'm circling here, if you can draw that picture and understand why that is, then we're in good shape. This piece right here, you can imagine this being the sampling distribution. Those where your estimators sort of end up. And of course, what you would like in the best case scenario, right, is you would like, let's see, I'll use a different color. It would be really nice if, in fact, you ended up right on top of the truth here, right? Really, really close. In which case, there is no 2. There's just number 1, which is the variance. That's all you have to worry about. And I've drawn a case where the variance is skinny. All right, let's go on and see. Let's do some examples and see if we can't figure out what's going on here. Here's a normal distribution, x1 through xn. They're independent, identically distributed. They come from a normal distribution with mean, mu, and variance sigma squared. We derived in the previous lecture the maximum likelihood estimator of the variance. So this is sigma squared hat, right? It's the estimate of the variance. And this thing is different than the sample variance. We all know the formula for the sample variance, x squared over n minus 1. The cool thing about the sample variance is that it's possible to show that the sample variance is unbiased. Okay, but I got a problem here. If the sample variance is unbiased, it has m minus 1, and this has n. This means that thing has to be biased. And in fact, that is indeed true. So the expected value of the maximum likelihood estimator of the variance is slightly less than the actual variance. And here's an easier way to think about it. It's 1 minus 1 over n. So there's a slight negative bias, but that bias goes away as the sample size gets very large. So that's nice to know. And we could even imagine that if the sample size was infinite, then in fact, the expected value of the MLE of the variance, that's going to converge to sigma squared as n gets big. Right? So that'll be consistent in some sense. You'll end up at the right target, but you always have a little negative bias. One way to imagine that is your estimates are always a little less than the truth. So you keep messing, keep underestimating, but you keep underestimating by just a little bit over and over again. Here's another one. We're going to come back to that example in a second, but here's another one. Let's look at a Poisson distribution. Here are x1 through xn is Poisson lambda. And the maximum likelihood estimator for the mean of a Poisson distribution is also the sample mean. And of course, by invariance, right, the maximum likelihood estimator of a function of x bar is also the maximum likelihood estimator of itself. Well, so that's a month. So the maximum likelihood estimator of gamma, which is 1 over lambda, is just 1 over x bar because I've plugged in the maximum likelihood estimator here. However, this estimator is biased, and that's because there's a particular interesting problem here. So here I say, well, what's the expected value of gamma hat? Well, let's try it. The expected value of gamma hat. This is a Poisson distribution, so it's the sum of the probability that the sample mean equals some number times 1 over that number. It's a weighted average of 1 over all the x bars, and you've got a sum over all the possible values that the x bars can take. Except in some cases, when that number is 0, you end up with 1 over 0, which is bad, which doesn't exist. So this particular thing doesn't exist because you're taking an average of a whole bunch of numbers. One of them is basically infinity, 1 over 0. So it doesn't exist. Because there's a chance that you may run a study and for Poisson distribution, you think about counting events. You may run a study and see no events ever. It's not likely very often to happen, but when it's possible, and because it's possible, when you take a weighted average of all the possibilities, you have to take a weighted average of 1 over 0, and 1 over 0 is undefined. So this expectation is sometimes written as equal to infinity to emphasize here that really this thing doesn't really exist. There's a bias, and you can't get a handle on how big the bias is. So we write it like this. Another set of important estimators are Bayes estimators. So let's compute some posterior estimators. So here's the standard Bayes setup. I have a bunch of data. And they come from some particular distribution. This is f of all the data given theta, and theta is my parameter of interest. And let's suppose I have a prior distribution, and I'm going to illustrate all of this in a second so you can see how we put this together. And then the posterior distribution is this thing. And so we use Bayes' theorem here to get that, right? And so if remember Bayes' theorem is probability of A given B is the probability of B given A times the probability of A all over the probability, right? Probability of B, right? Probability of B. And the probability of B is equal to the sum of the probability of B given A times the probability of A, but these are different A's. So these are AI's. These are all over all the different I's. So this is Bayes' theorem. And in this case, we have the continuous version rather than the discrete version, right? So I'm integrating out this particular thing. There is one, sometimes you see notation, these F's will emphasize what their parameters are. I'm not going to worry about that very much in the class. Just know that the F is a general function here, general density. So let's do an example. I think it's much easier to actually plug in for some of these things. So I'm going to let my X's be Bernoulli. These are just regular, this is a coin flip, right? Coin flip with the probability of a heads equal to theta. That's what this is. Well, if I have a bunch of Bernoullis, then I can add up how many coin flips, and that will be binomial. That's the same thing, binomial of n tries probability of success here. So that's what I have here. Now, what would be a good prior for my coin flip probability? Like, what's the chance? Is this 50%? Is it 75%? Is it 3%? Who knows? So we can imagine having a distribution. Let's imagine having a distribution over the unit interval from 0 to 1, and maybe that distribution goes something like this. Right? So you're more likely to be in the middle here, less likely to be at the edges. This is a type of beta distribution. You can get all sorts of distributions here under the beta by changing the parameters. You can even get uniform. So this is beta, alpha, beta here. So you can change the two parameters alpha, beta, and you can get different shapes. They can be all sorts of different interesting things. So this is going to be our prior here. And then what I'm going to do is I'm going to connect these things together. Well, so how do I connect it? Well, so the top of Bayes' theorem is this quantity, right? So the probability of A given B, right? Well, I think I actually used the flip. So let me go back here. Let me go back here. And oh yeah, A given B. So the probability of A given B is the probability of B and A all over the probability of B, right? And this B I can write as B given A times the probability of A all over the probability of B. So I'm going to do the same thing here. This is the top, and then I'm going to compute the bottom right here. So this is the top, and the top is, well, what is this? What is the distribution of Y given theta? Well, that's binomial. So that's this piece right here. And then I need to know what is the distribution of the probability of success. Well, that was this guy here, and that I've just written the formula out here. And you multiply them together, and some things will cancel. And actually, you can combine. So here, for example, I have a theta to the alpha minus 1. I have a theta to the y, so I get a theta to the y plus alpha minus 1, et cetera, et cetera. So that's going to be the top. On the bottom, it's slightly more complicated. I have to integrate this top piece over all theta, right? Because this looks like the top, but I'm integrating over all theta. And so I've written out the top piece here, and here's the part that depends on theta is here, and I have to integrate this. And the secret to this is to just recognize that, oh my God, hey, look at this. This looks like a beta distribution. This looks like a different beta distribution, right? You can look at it, right? You can compare it to this part right up here. This is theta to the alpha, 1 minus theta to the beta. Well, this is theta to a bunch of things, 1 minus theta to a bunch of things. So you look up this integral online, which is totally fine because I like to look things up online. And then this will equal to the normalizing constant of the beta. So that's that piece. And then this piece stays the same. So now I'm going to have to take the ratio, and then this is the bottom. So now I'm going to have to take the ratio of the top and the bottom. And certain things are going to cancel. Like, for example, we can see that, oh, right away, this is going to cancel here. And let's see, this part is going to cancel with this part, and that part is going to cancel with this part. And so I'm going to be left with this piece and this piece. And that's what I've got right here. Piece 1, piece 2. And so this is just a beta distribution. Again, so beta is a conjugate prior. So if I combine the beta and the binomial, I end up with a beta distribution. And the beta distribution has an interesting mean. So this is what's called, this is actually the posterior. That's a P, not posterior, posterior mean. And the reason it's called a posterior mean is because we've conditioned on the data. There's the data, that Y is the data. And we're learning about the parameter, the probability of success. So it's the posterior mean. And we can use that as an estimate. The posterior mean is it can be an estimate for theta. So you can use the maximum likelihood estimator, right? You can use the MLE because the data were binomial, and you can use Y over N, right? Which is the same thing as the sum of the X's over N, right? Remember that? The Y is the sum of the X's. Or you can do this. So we have competing cases. So we can use the posterior mean as an estimate theta, assuming that you have the data and that you have the prior parameters that give you the prior distribution on the probability of success. So here, let's observe some data. Again, here's the lowercase y, and I've just plugged that in. So theta hat is this thing. Now, I don't know about you, but in that form, that doesn't look particularly intuitive or helpful. So I'm going to rearrange it into, I think, a much more useful form. I'm going to break it into 2 parts. And so I can break it up into this guy here. That looks like my original theta hat. And this here, this is the expected value of theta to begin with from the prior. Remember that the prior says, ooh, on average, your theta is here. The posterior says, oh, now wait a second. After I observe some data, on average, I'm here. So we change from here to the posterior here. And so this is the prior. This is the prior mean. So what you're doing is you're taking a weighted average, and actually you can just write these as weights because these two pieces add to 1. So you're taking a weighted average of the MLE, this is the MLE, and the prior mean. And so you end up adding essentially a little bias because you know this thing is unbiased and you're adding in extra here. So now the expected value of theta hat here, this thing is going to be biased. All right. But of course that bias is going to go away over time because look at here, I'll use a different color. You will use orange. Look at where the sample size is here. So as the sample size gets big, the weight is going to go to 1 and you're going to end up with just that piece. So you're waiting for small sample sizes, you're waiting a little bit, you're adding in prior information, but as the sample size gets big, eventually this part goes away. Does that make sense? All right, I'll just get rid of that for a second because I'm going to come back to it. Okay, let's keep going here. So here's how I write about it. The posterior mean is achieved by shrinking the sample mean towards the prior mean. This is a type of a shrinkage estimator. It's a mix of the data estimate and the estimate based on prior information. Now, this is almost always true for Bayes estimators. They're almost always a mix of prior information and the data estimate. There's some exceptions. There's things called empirical Bayes estimators that use the data to estimate your prior information. And they always trade some bias for a reduction in variance. Almost always, I should say. And so sometimes the bias is large, but the resulting variance is very small. For example, if I used a constant to estimate something, the constant is never going to be equal to what I'm interested in. So there'll always be some bias, but the constant doesn't change. So if my constant is 7, if I estimate everyone's age to be 7, I have a biased estimator. It doesn't depend on the data, but it's a biased estimator. Its variance is 0, right? But its mean square error is certainly going to be positive because 7 is never going to be the correct answer on average. All right, so let's compare the plain old estimate, this thing, right? Where the expected value is this, and then the variance is this. This is just the regular old binomial variance, right? Right? This is, and some of you are used to using P, so I'm going to use P hat is an estimate of P, the probability of success, and the variance, of course, is P times 1 minus P hat over N. I'm just using thetas in this case. And then for our fancy new estimator, okay, this is the new one. This is the Bayes estimator. I'm going to use this thing. And so it's biased, right? And its mean square error is variance plus the bias squared. And so all I'm going to do is I'm going to plug in these formulas, and then I can go right to Wikipedia and I can calculate them. And here they are. That's the bias plus the variance squared. So if I want to compare this, basically what I want to do, so the mean square error from here is equal to just the variance, because you would add the bias squared, but the bias is 0 because it is correct on average. So you want the mean square error from the maximum likelihood estimator, and you want to compare it to the mean square error from the Bayes estimator. and their formulas are different. And so what I did is I'm going to pick, in order to draw this, I need to know alpha and beta. Otherwise, this is not a number. And one way to think about this is, suppose I see 5 out of 10 observations. Well, then p hat is equal to 0.5, and the variance is 0.5 times 0.5 over 10. So I can compute that, right? In this case, down here for the Bayes estimator, if I see 5 out of 10 observations, right? My estimate then is W times 0.5 plus 1 minus W times alpha over alpha plus beta. And so I need to know alpha and beta before I can compute anything. So to compare this approach, I have to pick these, and I'm going to pick these in a way that makes the mean square error constant. I'm going to just pick them. And that's achieved by using these things. Alpha equals beta equals the square root of n over 4. Now, in real life, you can pick any alpha over beta you want, and then you would compare, and I'm going to draw you a graph comparing the mean square error of these things. In this particular case, I'm just doing this as an example. Here's here, and I'm doing this because in the Casella-Berger book, they picked this for a particular reason, and there are pros and cons to holding the mean square error constant. Here, the mean square error, right, this is for the maximum likelihood estimator, is not constant, right? This is theta times 1 minus theta. So if I look at a graph, that's a function of theta, and theta is 0 here or 1 here, this is going to look like this, right? Because that's theta times 1 minus theta, which is theta minus theta squared. So it's going to be parabolic, right? And this scale will depend on whether, I'm dividing by n somehow and those sorts of things. And here, I'm holding the mean square error constant. So if this is the mean square error here, I'm going to get a line like this. I might be up here, I might be here. I want to see where it is. And the graphs on the next page show us exactly what's going on. So here they are. For 4 observations, you have the mean square error. So this guy here, this is the mean square error for let's see, actually, this is the mean square error for the maximum likelihood estimator, y over n. Same thing for this blue line here. This is the mean square error for the maximum likelihood estimator, not machine learning, maximum likelihood. This guy here in red, this is the Bayes estimator. And we've made it constant because we've picked alpha equals beta equals, well, what was it? Hold on. It was square root of, is square root of n over 4. Same thing here. Alpha equals beta equals square root of n over 4. Again, it's just an example. So what do we learn? What do we see from this? Well, for 4 observations here, the mean square error is much lower, right? When theta is, in a pretty big range. If theta is anywhere in between 90, let's say 0.9 and 10%, the mean square error is lower for the Bayes estimator. This is with 4 observations. If the true theta, this is the true, don't forget, this is the true probability of success. If the true probability of success is on the edges, so if it's out here or if it's out here, then you're going to prefer the maximum likelihood estimator. Now, as the number of observations grows, you're going to get the opposite. And so here, you're going to see something different, right? So here, that's where it's better. And in fact, that's where the Bayes estimate is better. And out here is better where the maximum likelihood estimate is best. So the Bayes estimate here and here is better. And one thing to note is that the expected value of theta, actually, all right, yeah, hold on. Actually, let me change the color so I makes it very clear. Under the Bayes estimator, the expected value of the proportion is alpha over alpha plus beta. So that's going to be root n over 4 over root n over 4 plus root n over 4, which is 1/2. So that Bayes estimator is assuming that the proportion, the true proportion, on average is right at 1/2. And so you tend to think it's near 1/2. Tend to think it's near 1/2. When you have small observations, near 1/2 is a pretty wide thing. When you have 400 observations, near 1/2 is much narrower. And so if you happen to guess right, if you happen to guess correctly for the Bayes estimator, and you guess somewhere that's closer, you can reduce your mean square error here and get a reduction. Although it's not a big reduction, you can get a reduction as opposed to the maximum likelihood estimator. But the maximum likelihood estimator is okay. When you don't have a lot of data, that reduction can be substantial. Here, for example, here we see this reduction is about half of that. So you cut your variance in half. This is why you would use things like this. All right, I think this is very good. One thing that so I think this is a good example. Again, try out the example, get comfortable with these ideas. These are important ideas. This bias variance trade-off is used to fit now virtually every machine learning model that we know of when we regularize or shrink. We're doing this type of bias variance trade-off. So we need to understand it in a simple situation here, and it will come back and we'll discuss it over and over again. One thing that I'm not going to talk about here is proving the consistency of the maximum likelihood estimators. So I am just going to tell you what the result is. I'm not going to go through it. Essentially, when you have a maximum likelihood estimator, theta hat, it's going to turn out that theta hat will converge to theta under some general conditions. And this turns out to be really important. We're going to define what theta is later. These are all properties of likelihood ratios, and I'm going to have a separate and optional video that will talk about what this particular section is, so we can go through it and understand it if you want to. So thanks for listening, and that wraps up this particular section.